Module 6 is the third of our 3 modules that deal with equilibrium problems. And this one is an interesting module because we're going to be talking a lot about how to alter the equilibrium state that's achieved, either through introducing perturbations to the equilibrium or by adding other equilibrium systems. So our learning goal for this lesson will be how two chemical equilibria can interact when they're both present in a mixture. Now, we've already seen some examples of how one can change an equilibrium state based on Le Chatelier's principle. Basically, if you add a reaction species, the reaction is going to shift to remove that species. If we remove a reaction species, it'll shift to add it back. If we change the temperature, the reaction will shift to absorb or release heat in response, as we've indicated it back in Module 4. If we change the volume of a reaction mixture, it'll shift to add or subtract gas particles. Finally, if we dilute a reaction mixture, the reaction could shift to add or remove solute particles. We didn't talk about that in a video, but it is part of the module. Now, one of the ways that we can do this is using something called the common ion effect. And we're going to illustrate this first dealing with solubility, and then later on in a different video we'll talk about how it may affect acid-base equilibria. But let's consider that solubility equilibrium. Remember, that happens when we have a salt or an ionic compound of some kind. I'll call it MXN. So M stands for a metal and X is for some anion that is attached to the metal. And it dissolves in water. It forms electrolytes. So it'll form a metal ion and some number of anions, some number of negative ions. And its equilibrium constant we call KSP. And it's just the product of the concentrations of the two species that are forming electrolytes. So if we were to take this situation and add one or the other ion, we could add both, but we just add one or the other, the equilibrium to respond must shift to the left and would create more solid of the original compound, the original MXN compound. If we were to remove some of those ions as they're being dissolved in solution, as they're being produced in solution, the equilibrium would actually act to dissolve more of the material, and so more of the MXN would dissolve. So you can think of this now as if we have something that we really want to dissolve in a solution and we want to dissolve more and more of it, all we need to do is find a way to remove those ions as they're introduced into the solution, and more of that solid will dissolve. We can also alter equilibria by combining them with other equilibria. Let me explain what that means. We're gonna be coupling equilibria together, and what coupling means is that they share a chemical species in common. So a really simple picture of an equilibrium would be maybe two people on a seesaw. Okay, they're going to find an optimal balance point, and that's something we could describe as their equilibrium. If we have two equilibria that are coupled together, it's a more complicated situation, so I would liken it to something like this. Here we have two seesaws, but there's one person in the middle that happens to be able to sit on both seesaws. So you can imagine now, you could probably find a balance point for this. It wouldn't be very easy, but you could. And this would be an analogy for two connected equilibria. The balance point that you would find would not be the same balance point as it would for either of the individual seesaws, but would be something that could satisfy both of the seesaws at once. So that's what happens now when we add these reactions together. So what I want to do is look at how the equilibrium constant is altered under different circumstances. So if we're adding two reactions together, reaction 1 and reaction 2, so the net reaction is the sum of those reactions. The net equilibrium constant is going to be the product of the equilibrium constants for each of the steps. If we were to reverse a reaction, the equilibrium constant becomes 1 over the equilibrium constant. And if it's multiplied by some constant a, then we got to raise the equilibrium constant to that power of a. So let's see how this works in principle with different kinds of realistic equilibria. So let's start with acid-base equilibria, and I've put the summary up in the upper right so we can refer to it. And let's say we want to know the equilibrium constant for something like this. All right, HNO2 plus hydroxide ion goes to water, and the nitrite ion, NO2 minus. So I've drawn what the equilibrium constant should look like. It should be the concentration of nitrite divided by the concentration of nitrous acid times the concentration of hydroxide ion. Now, another way you could look at this reaction, and this is something I hope that you'll begin to develop, is locate water in this. If water were one of the reactants, and if the two things that were on the product side were reactants, what would this reaction represent? Well, it would represent a base equilibrium for the nitride ion, because nitride is going to grab a proton from the water to form nitrous acid, HNO2, and a hydroxide ion. So all we've written here is the reverse of the Kb reaction for the nitride ion. Okay, well, that may be, but let's go ahead and work with this as acid-base equilibria. So we know that this is going to be true. This is the Ka for the nitrous acid. If it reacts with water, it's going to form a hydronium ion and a nitride ion. We also know that water undergoes this autoionization process with the equilibrium constant Kw. So I've conveniently labeled K1 as Ka and K2 is Kw. Now, if I want to produce the reaction at the top, I want to align the reactants and the products correctly. And I notice that, for example, hydroxide ion is in the reactant side of the top reaction, but it's in the product side of the second of these two reactions that I know. So I need to reverse that second reaction. So when I reverse that, I'll end up with basically what happens when we bring hydroxide and hydronium ion together. They make water. Okay, the equilibrium constant is going to be 1 over the Kw, and that comes directly from this summary set number 2, that reverse reaction causes the equilibrium constant to be 1 over the equilibrium constant. Since Kw is 10 to the minus 14, that means the equilibrium constant for this reaction is actually 10 to the plus 14. It's very strong. In other words, virtually all of this is going to go to the right-hand side. Now, when we add the first reaction, the HNO2 plus H2O, going to hydronium ion and nitride ion, we add that to the second one, the reverse of the second one, we'll end up with the reaction that we want, the one at the top. And in order to get there for the equilibrium constant, we have to multiply their two equilibrium constants. Now that comes from the first of the summary points. So that means we'll be multiplying and we'll end up with the very equilibrium constant that we were seeking in the first place. All right, we go through all of that because being able to manipulate these equilibria and determine what the equilibrium constant is going to be important for following what we do. Now, whenever we have multiple equilibria present in a reaction solution, there's usually going to be a dominant equilibrium, and that's the one that sort of dominates the result. It's one that you could basically say it's the one that's really going to determine what the final concentrations of all the reactants and products is going to be. And I want to use as an example of this a weak acid equilibrium. So, for example, in a weak acid like hydrogen fluoride, we know that this weak acid equilibrium exists where Ka is equal to 6.76 times 10 to the minus 4. Now, this thing is not the only equilibrium that's present in water, and we've been kind of glossing over this point, but the water autoionization is another equilibrium that's taking place at the same time, but it has an equilibrium constant of 10 to the minus 14. So in this case, because the Ka for the hydrofluoric acid is much larger, a factor of 10 to the 10th larger, it's going to be a dominant equilibrium in this case, and it's going to be the thing that really mostly determines what the concentrations of the various species are going to be. Now, this is actually only going to be true if we have a sufficiently large concentration of this to begin with. If we had a vanishingly small concentration of HF, it probably would not affect the water autoionization very much. But let's assume that we have an appreciable concentration of HF to begin with. How would we approach this? Well, the way to do it is you solve the weak acid equilibrium first, and you find the hydronium ion concentration. You assume that it's the dominant equilibrium based on the magnitudes of the equilibrium constants. You then test it. If that hydronium ion concentration is right around 10 to the minus 7, which we know is the concentration of hydronium ion in pure water, if it's within a factor of 10 of that, then it's probably the case that we have to solve both of the equilibria together. We can't just take one, solve it, and apply it to the other one. However, if the hydronium ion is not within that narrow range, then we could use that hydronium ion from the weak acid equilibrium, plug it into the equilibrium expression for Kw, and solve for OH minus, for example. as a result. So when you have a dominant equilibrium, it makes life a little bit easier because you could solve one equilibrium first and then just simply take those results and apply those concentrations into the second equilibrium and solve for whatever other quantities are in that second equilibrium that were not determined by the dominant equilibrium.